Okay. Hello. I'm going to talk you about the formation and evolution of atmosphere on early Titan. My name is Marounina, and I'm doing my PhD under the supervision of Tobie, Grasset, and Carpy. And this work was made with the help of Julien Monteux and Benjamin Charnay. Titan's atmosphere is a very massive atmosphere, and two of its main components, which are the methane and the nitrogen. Methane is destroyed by photodissociation or are lost to the atmosphere of Titan by escape, and its lifetime in the atmosphere is about 20 million years. And on the other hand, nitrogen was not accreted with the satellite, but probably converted from another nitrogen-bearing compound, which was probably ammonia. So the main question we want to address here are what is the origin of nitrogen and methane, and how have the composition of the atmosphere varied during Titan's history. Impacts have probably played a major role in Titan's atmospheric evolution. So first, they can bring or convert the volatiles needed to form Titan's atmosphere, or they can also erode Titan's atmosphere. So here you see a cartoon that presents the impact rate as a function of time. And you see that two of these mechanisms could be very active at the end of the accretion, where the impact rate was still high. And at this epoch, where they are an anomaly in impact rate, centered around 3.8, 3.9 billion years ago, which is called the late heavy bombardment. And today's impact rate is quite low. However, there still can be some episodic giant impacts who can influence the evolution of Titan's atmosphere. But here we study the early Titan, which means that we focus on the first billion year of its history. And I will present you a first model which investigates the evolution of the Titan's atmosphere during the late heavy bombardment, and the second model which investigates the emergence of an atmosphere at the end of the accretion. So the first model investigates the evolution of Titan's atmosphere under a high impact flux. So here you have a cartoon of an impact. You see here the impactor, here you have the atmosphere, and here you have the icy crust, which is partially enriched in ammonia. So typically the thickness of this layer in our model is between 1 and 5 kilometers. And when the impactor strikes the icy surface of Titan, it generates an impact pressure field. And thanks to the work of Cedex et al. 2011, we can connect this impact pressure field to the efficiency of the conversion of ammonia into nitrogen. So this way, we supply the nitrogen to the atmosphere of Titan. At the same time, we can erode this atmosphere by impact because here you have a formation of an impact plume where the molecules are heated and accelerated, and sometimes they are accelerated fast enough to escape the velocity of the body, the gravity of the body, sorry. And to take this in account, we use the parameterization of Shuvalov 2009. And finally, at temperatures and pressures of Titan, this atmosphere can partially condense at the surface. And to take this in account, we use the studies of Lorenz et al. 1999 and Charnay et al. 2014. So we do this computation for a whole population of impactors characteristic of the late heavy bombardment that we took from Charnay et al. 2009. And so here you have a map of the remaining ammonia at the Titan surface after one of our simulations. So black means that there are no more ammonia in the icy crust, and white means that the ammonia remain untouched. And I won't explain very much this picture, but it means that our surface at the end of the simulation was affected at least at 70%. So we firstly investigate if it was possible to form an atmosphere on Titan during the late heavy bombardment. And here I present you one of the simulations that are most favorable to the emergence of this atmosphere. So here you see the cumulated impactor mass that you can see as the advancement of the late heavy bombardment. And here you see the atmospheric mass divided by the present-day Titan's atmospheric mass. And we see that the atmosphere of the generated atmosphere does not exceed 6% of the present-day Titan's atmospheric mass. So we concluded that the formation of atmosphere, of a massive atmosphere during the late heavy bombardment was unlikely. And we also investigated the effect of the late heavy bombardment on a pre-existent atmosphere. So here you have the similar graphic that I showed you in a previous slide. And we see here the evolution of atmosphere that are 2 times, 5 times, or 7 times more massive than the present-day Titan's atmosphere. And this picture shows that these atmospheres are severely eroded during the late heavy bombardment. And we estimated that to sustain an atmosphere equivalent to the present-day one, we need the pre-LHB atmosphere to be at least 5 to 10 times more massive than today. So this picture summarizes our results. So if we had no atmosphere before the late heavy bombardment, during this event we generate only tenuous atmosphere, which implies that they were strong degassing after the late heavy bombardment to obtain the present-day Titan's atmosphere. And on the other hand, if we had an atmosphere before the late heavy bombardment, it was severely eroded during this event. This study also shows that the conversion of ammonia that is in the icy crust by impact is not very efficient to generate or sustain Titan's atmosphere, at least during the late heavy bombardment. However, there are other ammonia into nitrogen conversion theories. So you have the photochemical conversion, or the impact-induced conversion, but this time in the atmosphere during when the impactor comes through the atmosphere. And you have also the endogenic conversion. So these 2 theories depend on the condition of the atmosphere. And in the second study, we decided to focus on the pre-LHB atmosphere on Titan, so on the atmosphere at the end of the accretion, and to investigate its size and composition to see if the conditions meet those that are favorable to one of these conversions. So we suppose that the impact heating during the accretion was probably strong enough to melt Titan's surface. So we obtained a water ocean in equilibrium with the atmosphere. And to model the exchange between this water ocean and Titan's primitive atmosphere, we do this model. So we fixed the temperature and the mass of a molten material, and we suppose a split between a liquid phase and the vapor phase. And we first use the mass of the liquid and the temperature to compute a first pressure. So the problem is that this model is not conservative in mass and does not take into account a model of an atmosphere. That's why at the same time we use a model of an atmosphere that uses an atmospheric mass to compute a second pressure. And we check if the 2 pressures correspond. If they don't, we resuppose a splitting between a liquid and the atmosphere, and we do it until this condition is met. So in this model, we assume that we melt 5% of the total Titan's mass. And we do this model for 4 components, so the water, carbon dioxide, ammonia, and methane. And we take a volatility content compatible with estimation of Tobie et al. 2012. For the vapor-liquid equilibrium models, for the vapor phase, we take an ideal gas model for now, and Henry's law for a liquid phase. And for the atmosphere, we are modeling an isothermal atmosphere. So these are our preliminary results. So I present here 2 cases. The first one that is poor in volatiles in respect with the study of Tobie et al. 2012, and the other one that is more enriched in volatiles. And here you see that even in a case we are a low content in volatiles, we form an atmosphere of several bars. So here we are typically above 9 bars. And we see that in both cases, so here you have the total pressure, and you have the contribution of the carbon dioxide, methane, ammonia, and water here. And in both cases, the primitive atmospheres are predominantly composed of carbon dioxide and methane. And even when we increase the fraction of ammonia from here to here, its fraction in the atmosphere does not vary much, which means that the ammonia prefers to stay in the ocean, to stay dissolved in the ocean, and does not go much in the atmosphere. So here, for example, the maximum pressure of ammonia does not go above 0.5 bar. So here are our conclusions. So Titan's present-day atmosphere is not generated by impact during the late heavy bombardment, and pre-LHB atmospheres are severely eroded during this event. So they are the conclusion of our first model. And our preliminary results on a second model indicates that primitive atmospheres are mainly composed of carbon dioxide and methane, and ammonia is a minor component of Titan's primitive atmosphere. So as a future work, we want to improve our atmosphere-ocean model, and we want to take into account the Clatrate formation, which could change some of our results, and to finally investigate the efficient mechanism of ammonia into nitrogen conversion here. So, thank you.
We have time for 2 or 3 questions.
So this is I heard that there's another impact flux model. So there may be a late bombardment period, but not late heavy bombardment. The bombardment flux will automatically more lower than late heavy bombardment.
Yes.
So that due to the model the atmosphere.
It will change. It would not change the first conclusion. That means we still not generate an atmosphere on Titan. But however, if they were an atmosphere before the late heavy bombardment, we will not erode it that much as we do here. That will be the main difference.
So if you generate so much CO2 in this primordial atmosphere, where did that go? I mean, will we find CO2 ice then, if this were true?
That's a question, actually. It could be dissolved in the ocean, or maybe trapped in Clatrate. We don't know yet. We didn't think about it yet.
Okay, if no questions, we move to next. Oh, okay, one more question. Okay.
How did you scale the impact rate? Because on your graphs you say impact rate, and what we know of light-headed bombardment is scaled to the moon. And the Titan being further out in the atmosphere, I would expect the impact rate to be lower.
Actually, the study of Charnay et al. 2009, it is scaled to Iapetus.
Oh.
Yeah.
Okay,
Thank you.